Hi, and welcome to this sixth clip in the AQA Organic Chemistry series. And in this one, we're going to look at a process called cracking, and we're going to look at it in terms of the alkanes which are produced from the fractional distillation column. And if you remember, recapping several of the previous clips, we have this fractional distillation column which is cooler at the top and warmer, hotter at the bottom, and this has, as we've discussed previously, allowed us to fractionally distill a crude oil mixture and generate low boiling point fractions or low boiling point collections of molecules at the top of there and higher boiling point fractions down towards the bottom. And what we have worked out is that the smaller the alkane, the lower the boiling point will be, and the closer to the top of the column it will also be. What we've also discussed is the ease of ignition of a small molecule is higher than it is of a larger molecule. So a larger molecule is hard to ignite, and so if the primary use of a lot of fractions is to be used as a fuel for various forms, then having a fuel which doesn't light very well isn't particularly useful. And so for the purposes of fuel, what we find is that the ones towards the top of the column, i.e. the ones with a lower boiling point, which are smaller molecules, which are easier to ignite, and if they were to combust would probably do so in a complete fashion, then these molecules are going to be much more useful as a fuel. These are much more useful as a fuel. The ones down towards the bottom of the column are less useful as a fuel, partly, as we say, because they're harder to ignite and things like that. That's not to say they don't have a use. So some of these higher fuels are used in the shipping industry and in the air industry. The aeroplanes would use these larger fuels because sometimes it can be seen that we generate more energy from a larger one. It's just harder to ignite it in the first place. But by and large, the smaller the molecule is, the more useful as an everyday fuel it's going to be for what we would particularly want at home. So the generation of natural gases or the use of it as a natural gas at home and things like that will be much more useful if it's a small molecule. The problem with this is if we were to look at a pie chart of this distribution, the useful parts for what we would want would be a low percentage. The relatively less favourable fuels would be as a high percentage. And so we need to find a way of making these high percentage components of crude oil into potentially more useful products. And so we do so under the process of cracking. And so what I'll do is I'll just clear this page off and we'll have a look at cracking of a larger molecule. And so if we take in this example a large, relatively useless hydrocarbon, we'll take, how many carbons we've got here? We'll take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We'll take a carbon chain with 12 carbons on it. And for what we'll discuss today, we'll say that that's a relatively useless type of molecule in the fact that it doesn't burn very well, etc., etc. This will be a C12H26 molecule. Okay, so it's not going to ignite particularly well because it requires a lot of oxygen and things like that. And so what we have to do is a cracking process. And what we will do is we will take a boiling tube typically, and we'll take some sample of our fuel, our C12H26 molecule. So we'll put that here. We'll have to absorb that onto some glass wool or something similar. And we will put some blocks of a catalyst here. Now that catalyst will be what's known as a porous pot is one particular name you can see. You may also see phrases such as it's a zeolite catalyst or specific types of clay, but ultimately for the purposes of what we have here, this is a catalyst for this process. And we will, in order to make this process happen, we will heat this up. And so what we're doing here is we're heating our alkane in the presence of a catalyst. And we heat that up and it will evaporate, it will pass over our catalyst and it will undergo a transformation and it will proceed to travel along the tube, and we can then collect that product in another tube somewhere. We'll put that into a smaller test tube filled with water, as you would do from thermal decomposition experiments lower down, and we would collect that gas. And in here we would have a new product. Now that new product has been formed from the thermal decomposition, the cracking process of taking our C12H26 molecule, and through the process, as I say, of catalytic cracking, we've heated it, we've passed it over the catalyst, it's travelled down the tube, and we've collected it into here. Now that new product will have within it what's said to be a double bond, and what we have proceeded to make is a compound which now looks different to the previous compounds that we had in all of the clips up to this point. If you remember, all of the clips up to this point have included single bonds, like we have in that C12H26 molecule at the top of the screen there. This one has also changed its formula from, if you remember, from the CnH2n plus 2 formula, which we did in one of the very first clips. We had that generic formula there. Here we've lost that plus 2. We have now created a different compound family. If you remember, those previous ones were the alkanes. What we've done here is we've created an alkene. Specifically here we've created ethene because it's got 2 carbons. If you remember, eth meant 2, and so we've created this alkene family. And now this is a different type of chemical. This will have different chemical properties to the parent alkane that it came from. It's easy to see, it's shorter, so its boiling point will be much lower than the parent was. And what we've done is we've essentially cleaved off one end of the molecule, and we've created a C2H4 molecule. And this is, as we say, is going to have different chemical properties to the parent alkane, primarily due to the presence of this new feature here, this being a double bond. We've got 2 bonds between each of those 2 central carbons, and the presence of this double bond over all of the saturated bonds that we saw previously. This double bond is said to be unsaturated. This gives it new and different chemistry to the alkane family we've been looking at in all the previous clips. So in the next clip we will look at this new alkene structure in a little bit more detail. We'll look at the naming of a couple of them. We'll look at ethene and propene, for example, and then we'll look at what that double bond allows us to do, and we'll move through there into processes such as polymerization, addition polymerization, things like that in the preparation of polymers and more useful products. So thank you very much, and I will again see you in the next one.